Good evening, my dear students. I believe I am audible and visible to you. Well, it starts a bit late. It takes around 20 seconds to start. Welcome to the class. And today we are going to do an extremely important topic. Well, we have done the physical equilibrium, and I believe we have done it in very detail. Anybody has to ask any kind of question in the chapter, the topic which we have done in the previous class that was there on at 10 a.m. Anybody has to ask anything here? Good evening, Poonam, Tirthraj, Mayuk. Everyone has got the session link on the WhatsApp and the Telegram group. So I believe everybody would have joined. So now let's get along with the equilibrium constant. That is, we are going to talk about the chemical equilibrium. Now, NEET Elixir dropper batch is actually now shifted to 16th of August. So we are going to start on 16th of August and we can talk about the code as AV Live. So you are going to use the code AVLIVE to join the batch. Clear? So use the code AV Live and join the batch. Is it clear? Yes, Khushi, we are just starting it. The timings are already with you. This is the Elixir dropper batch. Now you are getting 46% off. And if you want to use the code AV Live, you are going to get an additional off. Clear? So that becomes 15,199. So you can use the code AVLIVE. Use it and go ahead. So here we have Elixir dropper batch. So let's begin over with the topic. So we had talked about the vapor liquid equilibrium and we have talked about what water vapor would be formed above the liquid surface. This is a vapor liquid equilibrium. And now we are going to get along with the thing called what is known as the active mass. Active mass. What exactly is the active mass? So two type of equilibrium, chemical and ionic, are studied for NEET exam. Yes, Mukund Singh. Ionic equilibrium we are going to do a bit later. We are doing chemical equilibrium at this moment. Okay. Mukund Singh, I believe you have not subscribed to the channel and you have not even liked the session. Go ahead and like the session. Subscribe to the channel and go with the unacademy.com/Anoop Vashishtha. Download the app and join with us. Okay. And join the group. Group you need to join is t.me/neet Anoop. Join this particular batch, and this is my phone number 77974. क्या था 797544141 अपना ही फोन नंबर भूल गया मैं. Send on this number a WhatsApp message so that I can give you the link of the WhatsApp group. And we are going to join that WhatsApp group and we are going to use that WhatsApp group for many things. Okay? Okay then. That's t.me/neet Anoop. That is my Telegram channel, and this is what we have the WhatsApp group. It's not necessary that the entire amount of the concentration of a substance present in the system takes part in the reaction. We have already done the chemical kinetics chapter, and there we talked about something called the active mass. Active mass is the term on which the rate of reaction is directly proportional. So the term on which the rate of the reaction is directly proportional is termed as the active mass. Okay? Clear? So the term with which that's clear. And the active mass is actually equal to the concentration raised to the power order. The number with which the concentration must be raised to get the active mass of the reactant is termed as the order. So this is what you need to remember and need to learn. And then we are going to talk about what the active mass is. Now, there are so many examples for the active mass. An example here we have taken that we want to construct a house on 100 square meter plot. And we find that the architect says that it will be completed in 6 months, considering 20 workers work for 8 hours each day. Now, what you can do is you can think about your mathematics and you say that if we work 40 workers, then the time would reduce to 3 months. 80 worker would make it 45 days, 160 in 22.5 days, 1600 in just 2.25 days. And if I use 4,000 workers, then the work would be completed in just 1 day. Okay. So you might be thinking that, okay, fine, why don't I just simply make 4,000 workers and make the rate of the reaction so fast that it gets completed in just 1 day? But actually, it doesn't happen that way. Why it doesn't happen that way? Because there are so many factors. It is not just the number of workers which is the important factor. There are so many other factors. Like various constructed structures, they might take time to get settled. Okay, there must be a sequence which is followed. It is not possible that one person is creating the floor and the other person starts putting the fan on the wall or maybe the lights. When the wall are not constructed, how are you going to put the lights? So building will not be constructed, Mayuk. It will fall only when after it is constructed. It won't even be constructed. Okay. And frankly speaking, 4,000 workers cannot even stand on 100 square meters. Forget about working on it. Is it clear? So that is the thing. The fact is, if you employ 4,000 workers, only 20 will be actually working and 3,980 would be idle. वो बैठे होंगे. Clear? So these 20 would become the active mass. अब अगर आप उसका लैंड का साइज बढ़ा दो, then the workers who can work also will increase. So active mass is not an absolute quantity. It is a quantity in comparison. It is not that if you take 1 mole per liter of a particular reactant, that will become the active mass. What we need to know is what is the concentration of the other reactants. Unless we know that, we won't be able to get the active mass. समझ आ रहा है बात? मुकुंद, अक्षय, Ananya, Mayuk. So that's what we have as the active mass. Any of the reactant in a particular bulk could be the deciding factor for the active mass. Any of the factor which is limiting, which is in controlled quantity, which is in the least quantity, that is going to decide the active mass. Is it clear? So active mass is the actual concentration or the amount of the reactant that is taking part in the reaction. Fine. The active mass of the reactant is decided by the concentration of the reactant present in the limiting amount. That is the least amount, which is going to determine the rate of the reaction, the factor which is going to determine how fast the reaction goes. Now, if all the reactants have comparable concentration, then the actual concentration becomes the active mass. In fact, actual concentration raised to power the order. Order actually takes care of that. Okay? So that is what we have as the limiting factors. The number of workers that actually work, the number of workers on which the rate of the formation of the house actually depends. That is what we have as the active mass. In case of the substances which have low concentration, their concentration itself becomes the active mass. And the substances which have much higher concentration, their active mass is found by multiplying the activity coefficient. Now that goes a little higher value. In NCRT also they have mentioned the word activity and fugacity for the gases. So I have mentioned it. The active mass is multiplying the activity coefficient by concentration. If the concentration is too high, the active mass becomes a constant throughout the reaction. If the concentration is too high, the substance becomes the solvent. And solvent is not used in the equilibrium or the kinetics equation. Is it clear? So that is what we have as the active mass. Now it becomes the definition of the word solvent. The definition of the word solvent. We have used the definition of the word solvent. Okay. Now we have the definition of the solvent. It is the substance which is present in a huge amount so that a small change in concentration. Remember, the concentration of the solvent does change and it can change. It is not that solvent, the concentration does not change. It can change, it does change, but the concentration is so high that its small change won't affect it. It's something like you are sitting in a room and another person sits in the room. You cannot say that the oxygen is getting low and that is why you are not able to breathe. Okay. Not necessarily, Mayuk. In case of chemical kinetics, the definition becomes a little bit different. The definition of the solvent is dependent on the reason we are talking about. So in case of chemical kinetics, we talk about, okay, fine, we are going to change the concentration of this substance slightly. Will it affect the rate of the reaction? If it doesn't, it becomes a solvent. Clear? So now we have the Goldberg and Waage law, and that is also known as the law of mass actions. The Goldberg and Waage law, or the law of mass actions that we already understand, is that the rate of the reaction is directly proportional to the product of the active masses of the reactant. So that is how we have defined the active mass as well. The term or the factor on which the rate is directly dependent. Okay, or directly proportional. So that is Goldberg-Waage law, or the law of mass actions. Okay. Now, when we are talking about the chemical equation, chemical equilibrium, we are talking about this particular equation. So here we have a simple equation having two reactants and two products. Okay. This is the general equation, that is what is written. Now this is a chemical equation. These two reactants and the products, they are chemically different. Okay. The reactants and products are chemically different. Now we have used this particular arrow. Okay. Now this is what we call as the equilibrium arrow. Fine. This is a combination of half arrows pointed towards right and left. What each arrow represents? It represents the direction of the reaction. The top arrow represents the direction of the forward reaction. Okay. The bottom arrow shows the direction of the backward reaction. The length of the arrow talks about the speed of the reaction, relative rate of each reaction. The length of each arrow is the same. That means the forward and the backward reaction, they are taking place at the same speed. And then the reaction is equilibrium. Now it becomes the equilibrium arrow. Be very clear, we can even have the reaction like this, which says that the rate of the forward reaction is much higher than the rate of the backward reaction. We could even have like this, which says the rate of the backward reaction is much higher than the rate of the forward reaction. And when we talk about this reaction, this arrow, it simply says that the backward reaction is so slow that it can be considered that only the forward reaction is taking place. So even arrow tell you a lot. Is it clear? Where are the students? We have only six students watching here. Again, we have got back to the same case. No props. Let's see. No, there is a problem, but let's see. We'll finish off the topic one by one. Okay. So this is what we have as the equilibrium error. Tomorrow at 4 p.m. we are having the bonding class, and tomorrow 1 p.m. we are having a strategy session, whether you need to sacrifice your sleep to clear the NEET or not. Let us see whether you need to sacrifice the sleep or not. Many of the students say, सर मुझे कितनी देर सोना चाहिए, क्या मुझे जागना चाहिए, क्या मेरी नींद की वजह से प्रॉब्लम हो जाएगी? Let's see tomorrow at 1 p.m. Okay, so that is what we have as the equilibrium arrow. Now you need to remember one little thing. There are many things that you get confused with. Is the Goldberg and Waage law that we do in the equilibrium chapter, is it the same as chemical kinetics? But when we talk about the chemical kinetics, we say it is the orders. And here equilibrium, we say stoichiometric coefficient. Then how does it become the same? The Goldberg and Waage law, the law of mass action, whether it be chemical kinetics or whether it be the equilibrium chapter, is exactly the same. There is no difference in any of these two. Okay. A number of live students trying to revert back to the equilibrium. Okay. Have you shared this with your friends? Now, we can say there is something called the rate determining step. We have discussed about the rate determining step earlier. Okay. We have already discussed about something called the rate determining step. This is the slowest or the most difficult step in the entire reaction. That is what we have as the rate determining step. The entire rate of the reaction would depend on the speed of the slowest step. Fine. Now, an equilibrium equation always represents the rate determining step. Fine. It represents the single step, the elementary step, the rate determining step of the reaction. Okay. So you had not shared the session as yet. You should have shared, isn't it? शेयर करने के बाद बच्चे और कम हो गए। तो शायद वो शेयर करने के लिए गायब हुए थे। ओके, ध्यान रखना द इक्विलिब्रियम इक्वेशन ऑलवेज रिप्रेजेंट द रेट डिटरमाइनिंग स्टेप, दैट इज इट रिप्रेजेंट्स द एलिमेंट्री रिएक्शन. I have told you in the chemical kinetics that the elementary reaction, the stoichiometric coefficient become the orders. So for the equilibrium equation, the stoichiometric coefficient themselves are the orders. ओके तीर्थराज, उन फ्रेंड्स को भी कह दो कि ये जो टॉपिक हम कर रहे हैं दैट इज इंपॉर्टेंट फॉर इवन जेई. ओके, दे आल्सो कैन अटेंड द सेशन and they can join the Unacademy JE batch using the code AV Live. No problems with that. Is this clear? Cyan has dedicated a hat to me, and that's Teacher's Day hat, 4 hours ago. Maybe he had the Teacher's Day hat. Do you know when you attend the special classes and the plus classes, you get some minutes, and with that, you get some hats which you can dedicate to the teachers. So go ahead and attend the special classes and earn those hats. Okay. So that's what we have as elementary reaction. And in case of elementary reaction, the stoichiometric coefficient represents the number of species of each kind actually interacting in the step in an instant. And that is the reason when you change the balancing of the equilibrium equation, you actually change the mechanism of the equation. And that is why the expression changes. Is that clear? Mayuk, you need to know that. Okay, nobody tells you that. That is why you didn't know. Okay. The number of chemical species, that is the atoms, molecules, or ions taking part in a single step, or I should say the number of independent. The number of independent chemical species, that is the atoms, molecules, or ions taking part in a single step of the reaction, is termed molecularity of that step of the reaction. Okay. I believe you have got the information that at 8 p.m. today we have the quiz of the chapter called metallurgy. Okay. Forget it, many of the teachers don't know. Okay. So that's termed molecularity of that step of the reaction. And for a single step of the reaction, the molecularity of step itself is the order. Clear? For a multi-step reaction, the molecularity of the rate determining step is the order of the reaction. So what exactly this tells you? This simply tells you that in the case of equilibrium equation that we are talking about, the molecularity, the reaction stoichiometric coefficients, they represent the order of the reaction. Okay. The active mass is not just the concentration. It could be less than the concentration. It could be even more than the concentration because we are going to raise to the power the order. The active mass is determined experimentally. The number with which the concentration must be raised to get the direct proportionality of the rate on it, that is the active mass, is termed the order with respect to the given reactant. So that is what we have as a definition of the order. And in the light of the present observation, the Goldberg and Waage law, that is the law of mass action, can be written as for equilibrium. The rate of reaction is directly proportional to the product of the concentration of the reactant raised to power their respective stoichiometric coefficients. Okay, for equilibrium equation representing rate determining step. Is this clear? Equilibrium equation is considered to be the rate determining step, so this statement is specifically valid for the equilibrium. Now for the equation A of A plus B of B giving you C of C plus D of D, okay, you can write it PQRS also, the stoichiometric coefficient doesn't make a difference. The rate of the forward reaction, the rate RF would be proportional to concentration of A raised to power A, concentration of B raised to power B, because these are the active masses. Now we can even talk about the backward reaction. Now remember, in case of any of the equation, right side is the product. The left side is the reactant. If the reaction is going from reactant to the product, that is left to right, we say the reaction is going in the forward direction. If it is going from product to the reactant, we say the reaction is going in the backward direction. Any confusions here? Everybody who has joined the session has liked the session? We have got only 7 students again. कहीं पे कोई और क्लास चल रही है क्या इस समय? Any doubts? So that's the rate of the backward reaction and the forward reaction. Now these are proportionalities. To convert the proportionality into equality, we need the constant, and that constant would be called the rate constant. Rate constant, velocity constant, specific rate. We have done the definition in the chemical kinetics chapter, remember? The rate constant or the velocity constant or the specific rate is the rate of the reaction when the active mass of each reactant is 1. Maybe शायद उनका खत्म हो गया है. Okay. हमारे पास सारे वेस्ट बंगाल के स्टूडेंट है. तो प्रेरणा आधा आपका भी खत्म करवाते हैं हम. And today, remember, at 8 p.m. we have the special class. Remember that. Okay. So the rate constant or the velocity constant or the active mass of each reactant is 1. So we have just talked about this as the rate constant of forward reaction. And this is for the backward reaction. Okay. Any confusions till this point? अक्षय हमारे पास इस समय सिर्फ 5 स्टूडेंट है बेटा. किसी को कुछ पूछना है? Anything anybody has to ask? We have Mayuk Sen Gupta, we have Tirthraj Mukherjee. We have Priyanshu Ghosh. Out of 5, we have 3 students from West Bengal. है ना? Prerna Rajput, Akshay Thakur. These are the 2 students who are from North Belt. Prerna Rajput and Akshay Thakur. Okay. So like it. Anyone has to ask anything here? When we say the reaction is at equilibrium, it means that whatever reaction is taking place in the forward direction, the same reaction is taking place in the backward direction as well. So that whatever amount of reactant is consumed to form the product, the same amount of reactant is formed by the consumption of product. Whatever reactant is consumed, the same amount of product reactant is formed. Whatever amount of product is formed, the same amount of product is consumed. Is that clear? So that is what we have as the rate of the reaction. Okay. So the concentration of the reactant and products becomes unchanging. Now, most of the books say the word constant. There is nothing wrong with the word constant. It is absolutely right. But the problem is that the student, whenever they hear the constant word, they feel like the constant is some number and everything is equal to that. It doesn't happen that way. Constant means it does not change with time. So I am using the word unchanging. The concentration of the products becomes unchanging. The concentration of the reactant becomes unchanging. Unchanging means constant, but people get confused with that. And I really fear the confusion of the student. Anybody has any kind of confusion, ask it right now. Yeah, no net change takes place. It's not that the reaction is not taking place. The only thing is no net reaction is taking place. The rate of the forward reaction and the rate of the backward reaction become equal. Okay, I hope nobody is getting confused with it. I prefer to use the word unchanging. Okay, rate of the forward reaction is equal to the rate of the backward reaction. So this is the expression for the forward reaction. This is the expression for the backward reaction, and they are equal. They are equal to each other. Is it clear? Ananya Sarkar, don't miss the word net. Ananya Sarkar also is one of them. So I have all the students from West Bengal only, or at least Bengali students. Okay, fine. Now we have just shifted it. So what happens? We take this particular part and we take it in the denominator. We take this part, we take it here in the denominator, and we get kf upon kb is equal to c raised to power c, d raised to power d, a raised to power a, b raised to power b. Now kf and kb are rate constants. They are not going to change unless we change the temperature. We are not going to change the temperature. These are not going to change. So their ratio kf and kb also is a constant. Now this ratio of kf and kb is called the equilibrium constant. Is this clear? So this is what we know as the equilibrium constant. Ansari Misbah, beta, what does the difference between what? मैं समझा नहीं क्यों क्वेश्चन क्या है? Fine. What is the ratio of the forward reaction rate constant to the backward reaction rate constant? It's termed as the equilibrium constant. Fine. Now remember, this in turn is equal to ratio of the product of the concentration of the products. Ratio of the product of the concentration of the products raised to power their respective stoichiometric coefficient. Okay. 2. The product of the concentration of the reactants raised to power their respective stoichiometric coefficients. Okay. That is what we call as the equilibrium constant. Any confusions with that? Fine. So that is the equilibrium constant. Now please remember one thing, that the equilibrium constant is merely calculated from the concentration at equilibrium. It does not depend on the concentration at equilibrium. Okay. It's something like when we talk about the gravitational constant, we can calculate the gravitational constant by knowing the two masses, the attractive force, and the distance between them. But do you ever say that the gravitational constant is proportional to mass? No, it is not. It has absolutely nothing to do with mass. Gravitational constant is a constant. It's a universal constant. Fine. In the same manner, when we talk about the equilibrium constant, it does not depend on the concentration at equilibrium. It's something like that there is a pole or tall bridge. Okay. There is a tall place, tall plaza, which we call. You are driving and you say, I have reached the toll plaza. My location is the location of toll plaza. Now, location of the toll plaza does not depend on your location. You have reached there. In the same manner, when we talk about the concentration at equilibrium, the concentration has reached equilibrium. That is why we can use the concentration to find the equilibrium constant. Equilibrium constant does not depend on that. Your location, the toll plaza location does not depend on your location. The toll plaza will stay there even if you move further or backward. Is it clear? Fine. So just remember. Now let's talk about the characteristic of the equilibrium constant. What are the various characteristic of the equilibrium constant? The very first thing, the equilibrium equation represents the rate determining step. Hence, the stoichiometric coefficient are the orders with respect to each of the reactant that are being used in the equilibrium constant. Is it okay? If the equation is multiplied by a number, any number, all stoichiometric coefficient change and equilibrium constant for the new equation would be the old equilibrium constant raised to power the number with which the equation was multiplied. Okay, let us say we have the equation of A plus B of B in equilibrium with C of C plus D of D. The equilibrium constant would be K. Equilibrium constant would be equal to the concentration of C raised to power C, concentration of D raised to power D divided by concentration of A raised to power A divided by concentration of B raised to power B. That will be the equilibrium constant. Okay. Now what I do is I multiply the entire equation by 2. So I make it as 2AA plus 2BB in equilibrium with 2CC plus 2DD. Okay. Now the equilibrium constant, that will, let's say K dash, would become equal to concentration of C raised to power 2C, concentration of D raised to power 2D. divided by the concentration of A raised to power 2A multiplied by the concentration of B raised to power 2B. So in fact, it's going to become equal to K square. Am I clear with that? Anybody has to ask anything here? This is a peculiar class in which I actually know the names of all the students attending the class. Okay. Mayuk, Akshay, Tirthraj, Prerna, Priyanshu, Ananya, मिस्टर अननोन सेज कोई है यहाँ पे क्या पूछने आए हो बेटा मैं हूं okay Mr. Unknown, first of all like the session and then we are going to discuss further. So you need to remember that by multiplying the equation by any number you actually change the reaction and you change the mechanism, you change the rate determining step. Okay, you change the RDS, you change the order, and so quite obviously you change the equilibrium constant. मिसबा ये नोट्स मिलेंगे आपको टेलीग्राम चैनल पर and the WhatsApp channel also. Okay, you are going to get these notes on the WhatsApp group and the Telegram group. So the equilibrium constant for the equation is A plus B, C plus D will be K1 is equal to C D upon AB. And if I multiply it by 2, it's going to actually become the square. Hello, Desire. So K2 is equal to K1 square. Any confusions, anybody? Where is the link for what? The link is there in the description of the YouTube, or you can join t.me/NEET Anoop. Or you can message me at 7975 कर रहा हूं मैं यार फिर नंबर भूल गया 7975441411. So you can just message me on this number WhatsApp and I'll give you the link of the group. Okay, so this is K2 is equal to K1 square. Second point, it does not depend on the concentration of the reactant or the products or their partial pressures. Clear? I just told you that these are used to determine the equilibrium constant. They do not depend, the equilibrium constant does not depend on them. Is it clear? Is that clear? Further, it does not depend on catalyst nature or amount. Equilibrium constant does not depend. Rate constant depends on that. The fact is, when you add a catalyst, then in that case, it changes the rate of the reaction for the forward as well as backward reaction by the same factor. So if the rate of the forward reaction doubles, the rate of the backward reaction also doubles. So addition of the catalyst does not change the equilibrium constant. It only makes the equilibrium achieve faster, easier. So by addition of the catalyst, equilibrium is achieved faster. It's something like that you place a staircase. So staircase not only facilitates the movement from ground floor to the top floor, it also facilitates the movement from the top floor to the ground floor. So both ways it facilitates equally. Okay. It doesn't mean that if you put a staircase, then the more people will start staying upwards. They won't stay there. They would go there, but they won't stay there. The equilibrium would be again maintained. Okay. Clear? The catalyst does increases both the forward and the backward reaction rate by the same factor. It does not change the equilibrium constant or even the equilibrium position, but makes the achievement of equilibrium easier and faster. So that is the purpose of the catalyst. It does not affect the equilibrium constant. Fine. Same for poison. The poison is different. Poison acts on the catalyst. You are using the word inhibitor and you are thinking about the poison. Poison affects the catalyst. Activator affects the catalyst. Inhibitor affects the reactant. Catalyst affects the reactant. Is that clear? Now let's talk about the effect of temperature. Now this effect of the temperature we have actually discussed in chemical kinetics. See, many of the things are coming from chemical kinetics and thermodynamics. Increasing the temperature of any chemical reaction increases the rate of the reaction, irrespective of it being heat consuming, that is endothermic, or heat releasing exothermic. So the rate of exothermic reaction also increases with temperature. You can see a very simple example. You take a paper piece, you burn it. Now, if you heat it further, it is going to burn faster. Burning is an exothermic reaction, but it takes place even faster as you increase the temperature. Clear? Now, the problem with temperature is it increases the rate of forward and the backward reaction unequally. Clear? It increases the rate of the endothermic reaction more than the rate of exothermic reaction. The reaction which has a higher activation energy, it is affected more by the increase in temperature rather than the factor, the species which has low activation energy. Is it clear? Don't be sorry about it, Mayuk. You can make this mistake. That is obvious, normal. Is this clear? So that's an example written here. I believe you can relate to that example. As the temperatures increase, the rate of the reaction increases. With each increment in temperature, the increase in rate with respect to the present rate keeps on decreasing. And the exothermic reaction is easy and fast, while the endothermic reaction is difficult and slow. So the effect of increase in temperature and the rate of endothermic reaction is more than the exothermic reaction. So that simply means if we increase the temperature, the rate is going to increase for the forward as well as backward reaction. The equilibrium is going to take less time to be achieved, and the reaction will overall shift in the endothermic reaction. Okay, so increase in temperature makes achievement of equilibrium easy and fast. Okay, it makes the achievement of equilibrium easy and fast. Fine. The overall reaction shifts to the endothermic direction. Is it clear? the overall reaction shifts to the endothermic direction. Any confusions, anybody? Fine. Okay. Any confusions here? That effect of the temperature? Is that very much clear? I'm telling you this particular statement many a times because the student generally later on they just get confused and they forget this particular statement and simply write in the question something else. This question has been asked many times. With increase in temperature, the rate of the forward reaction increases, the rate of the backward reaction increases, the rate of the endothermic reaction increases, the rate of exothermic reaction increases, the rate of both the reaction increases, the rate of endothermic reactions more, the rate of exothermic reaction increases more. This type of options are asked. As the overall reaction will shift towards the endothermic reaction. If the forward reaction is endothermic, then the reaction will shift towards forward direction, that is product. And if the reaction, if the and the value of equilibrium constant will increase. Okay, increase in temperature increases equilibrium constant of endothermic reaction and decreases decreases equilibrium constant of exothermic reaction. Is it clear? If the forward reaction is exothermic, the reaction would shift towards the reactant and the value of equilibrium constant would decrease. Now let's talk about the dimensions of equilibrium constant. What would be the dimensions of equilibrium constant? Okay. Now, when we talk about the dimensions of the equilibrium constant, when we talk about the sum of the stoichiometric coefficient of the reactant and product, they may be same, may be different. Okay. So C plus D may be equal to A plus D, and C plus D may not be equal to A plus D. So we are going to have the concentration raised to power the stoichiometric coefficient, and the concentration are not dimensionless quantity, they have dimensions. So there is a possibility that equilibrium constant has a dimension. Okay. But now the equilibrium constant is used in many equations such as exponent or log where dimensions are not allowed. So we will have to make equilibrium constant dimensionless. Now how do we make the equilibrium constant dimensionless? Anyone has to ask anything? Everyone who's watching the session has liked the session? Clear? Is this clear? So now what we do is we take the equilibrium constant in ratio. Like what we have is, let's say we have the concentration as 5 mole per decimeter cube, and we have the standard as 1 mole per decimeter cube. So if I take the concentration by standard, it becomes 5 mole per decimeter cube divided by 1 mole per decimeter cube, and that simply becomes equal to 5. So if we take the concentration and partial pressure in the standard units, they would become dimensionless. Is that clear? So they are going to become dimensionless if we talk about the units, the dimensionless. Clear? Any confusions? Similarly, the partial pressures are taken with respect to 1 bar and again become dimensionless. Clear? So equilibrium constant in which all concentration are in standard units is dimensionless. Is it clear? Fine. But we still put certain dimensions sometimes. Now it is just to clear the units in which the concentration is to be expressed or measured. But if you think about atmosphere, then in that case, atmosphere is not a standard unit, so it is going to be dimensioned. The change of measuring unit does not change the magnitude of the equilibrium constant. Clear? Now just remember, equilibrium constant is a positive real number. It cannot be imaginary. It cannot be negative. It can, of course, be fractional, but it's a real number because it has concentration. Concentrations cannot be negative, but it has a range. Theoretically, it can be from 0 to infinity. Okay. Now, what does the magnitude of equilibrium constant tell us? If we have a very small equilibrium constant or a very large equilibrium constant, what does exactly it tells us? Now, these are the questions which have been asked, that this is the magnitude of the equilibrium constant. What does it mean? Okay. Now we need to be clear that the equilibrium constant is the ratio of the concentration of the product and the reactant at equilibrium. If the value is greater than 1, it would mean that the concentration of product at equilibrium is more than the reactant. That is numerator, which is the product of the concentration of the products is greater than reactant. Numerator is greater than the denominator, I should say, not reactant. Is it clear? Now, this also means that products are more stable than the reactants under the given set of conditions. That is why more products are formed than the reactants being left in the reaction. Okay. More is the magnitude of the equilibrium constant, greater is the magnitude from 1, more it shifts towards the equilibrium, the completion. Higher is the magnitude of equilibrium constant, more towards the completion it shifts, and for very high value, it is considered single-sided reaction. And in that case, we don't put the equilibrium arrows, rather we simply put a single arrow. So the reaction is shifted only in one particular direction. Anyone has to ask anything? A value between 0 and 1 would mean that the reactants are more stable than the products. The reaction is shifted towards the reactants. The backward reaction is more. So the reaction would be shifted to the reactants. Less of the product is going to be formed. Clear? Now, if we get the value of 1, equilibrium constant is 1, then that would mean delta G naught of the reaction is 0. Delta G naught is 0. Then the equilibrium constant is going to be 1. Because delta G naught is equal to minus 2.303 RT log the equilibrium constant. So the value of equilibrium constant as 1 would mean delta G naught is 0. There is no change in free energy of the conversion of the reactant to the product. Okay. And that happens, yes, this kind of a reaction is there, where the reactant and product have exactly the same stability, so that when they reach equilibrium, the reactant and product are going to be present exactly in the same concentration. And that is what we have as the optical isomers, that is enantiomers. Enantiomers have exactly the same thermodynamic stability. So if they are capable of converting into each other, we always end up with the racemic mixture. That is, we have the same concentration of the reactant and product. Okay. Delta G is equal to 0. Delta G naught nahi. Delta G naught is standard. Understand the difference between delta G and delta G naught. Okay. At equilibrium, delta G is 0, not delta G naught. Delta G naught has been defined for the completion of the reaction. It's not defined as equilibrium. But getting the value of delta G naught, we can get the position of equilibrium. समझ आया तीर्थराज? Now remember, equilibrium constant is a ratio at equilibrium. But the reaction is not going to be equilibrium every time. Okay. It is going to initiate somewhere. It is going to end somewhere. It is going to be some time in between also. So equilibrium constant is not just that. There are many points from initiation to completion. Fine. So there are many points from initiation to completion. Now, this ratio, which is calculated at any point other than equilibrium, is called the reaction quotient. Okay. The ratio at any point other than equilibrium or even at equilibrium, we can call it reaction quotient. But overall, we can say K is equal to 1. How do we say K is equal to 1? Overall, Mayuk? No, no, we cannot say K equal to 1 for starting to end. That is not K. K is at equilibrium. At equilibrium. You can't take the average of K. Fine. So it's something like it's saying that the age of a person is 1. The overall life of a person is 1 because we are taking about the average from 0 to 1. Yeah, reaction quotient is denoted by Q. Okay. The reaction quotient Q is the ratio of the product of the concentration of the product raised to power the power, the respective stoichiometric coefficient, to the product of the concentration of the reactant raised to the power the respective stoichiometric coefficient. Now, instead of at equilibrium, it becomes at any point in the reaction. So there are infinite reaction quotient for any reaction. At each instant, there is one particular reaction quotient. Is this clear? Just remember today 8 p.m. we have a class and we are going to do the questions of the chapter called metallurgy. Okay, so Q has the same expression as K. The only thing is here we are not writing at equilibrium. Now the value of Q can be greater, can be less or equal to the equilibrium constant. Is this clear? Now if Q is equal to K, that means the reaction is at equilibrium. So K is Q at equilibrium. Now, if it is at equilibrium, that means the reaction is not going to shift by its own. You can shift the position, but you will have to make an effort for it. Okay. Reaction does not have a tendency to shift by itself. Is it clear? Now, if Q is less than K, at this point, the reaction would mean the concentration of the product is lower than what it should be at equilibrium. Okay. So, reaction shifts towards products. To be at equilibrium, numerator should be increased, and that numerator is product. Is this clear? So if Q is less than K, it would mean the concentration of the product is lower than it should be at equilibrium, or the concentration of reactant is more than what it should be at equilibrium. So reactant needs to be consumed, the product needs to be formed, the reaction should shift in the forward direction. Is this clear? So if Q value comes out to be less than K, the reaction shifts in the forward direction. Yes, more product formation will take place. Now, if Q is greater than K, that means we have somehow made the product more than what it should be at equilibrium. And if the product is more than what it should be at equilibrium, then the product would be consumed and the reactant would be formed. Okay, so product consumed, reactant formed. Okay, so here it is, backward. Backward means towards reactants. Is this clear? This means that to attain equilibrium, the reaction would like to shift towards the reactant, that is in the backward direction, away from the product. Clear? Now the reaction quotient changes with the product. Now what happens? If in a reaction you add the reactant, you increase the concentration of the reactant, the reaction will shift forward. Okay, now we are talking about the effect of the change in concentration of the reactant and product. With addition of the reactant, the denominator of the expression increases and Q becomes less than K, the reaction shifts in the forward direction. If you add the product, the numerator of the expression increases and Q becomes more than K. The reaction shifts to the backward direction. So addition of the product shifts the reaction backward. Addition of the reactant shifts the reaction forward. समझ आ गया ये? किसी को कोई दिक्कत? Now, removal has the opposite effect. If you remove the reactant, the reaction will shift backward. If you remove the product, the reaction will shift forward. Now, these things are to be known because many of the reactions we change the reaction, we shift the reaction by adjusting the concentration of the reactant product, like Haber's process of manufacture of ammonia. We actually deliberately remove ammonia by liquation and we keep on increasing the concentration of hydrogen and nitrogen. So that shifts the reaction in the forward direction. Clear? Now let us see how the reaction quotient changes with pressure. Check out these reactions. Now all are gaseous reaction. All are homogeneous gaseous reactions. Noted them down. Now let's talk about the first reaction. Its equilibrium constant is concentration of Hi raised to power 2, concentration of hydrogen and concentration of iodine in the denominator. Let us consider X, Y, and Z as the reaction at equilibrium. These are the equilibrium concentration. These are the equilibrium concentrations. Now, what we do is we have the reaction taking place in this kind of a container. Now, this has a piston over it. It's movable piston. What we do is we make the pressure is P, we make the pressure 2P. The moment we make the pressure 2P, the piston is going to move down. Here the volume was V, the volume becomes V by 2. Is that clear? Now, if we decrease the volume, keeping the mass same, we decreased, keeping mass same. Means it is still a closed system. We are not talking about open system, we are talking about a closed system. The concentration are going to double. The concentration simply double. Whether it be reactant, whether it be product, the concentration of everything increases to double. Now, since we have made a change, we find the value of Q. What we find? The value of Q comes out to be the same. So that means increase in pressure does not affect equilibrium for this reaction. Any confusion, anybody? Now what I do is I do reverse. I shift the above and I make the pressure P by 2 and the volume 2V. So what happens? If the volume is increased, the concentration, the partial pressure, everything becomes half. So it becomes at P decreased, V increased. Overall energy or overall mass? Increase in pressure does not affect the equilibrium. Now let's talk about what happens when we decrease the pressure. Decrease the pressure, we make the concentrations half. If we make the concentrations half, then in that case the Q is this, and we find that Q is again the same. This is the equilibrium constant for the reaction, Z square upon XY. On increasing the pressure on the piston, it moves down, decreasing the volume. If the volume is suddenly made half, the number of moles of each reactant and product remains constant while the concentration suddenly doubles. What is concentration? Moles divided by volume. Moles remain the same, volume becomes half. The concentration doubles. Mass remains same, Poonam. We are not allowing the substances to escape out. We have kept it the closed system. We have the piston. It increases the pressure, decreases the volume, but the mass remains the same. Okay. Now, if I find the reaction quotient remains the same as the equilibrium constant. That is the same as the equilibrium constant. It simply means the increase in pressure, which leads to a decrease in volume, and increase in concentration has no effect on the reaction. It stays at equilibrium. Fine. So this particular reaction does not change with pressure change. If the pressure is decreased on the piston, it moves up, increasing the volume. The volume is made double. The number of moles remain again the same. The volume is double. The concentration becomes half. We put it as reaction quotient Q. Again, it comes out to be the same as the equilibrium constant. So what does it mean? The decrease in pressure, which leads to an increase in volume and decrease in concentration, has no effect on the reaction. The equilibrium does not change. Let's talk about the next reaction. What can you say about this reaction? Think over. What can you say about this reaction? Priyanshu, this is another reaction. Check it out whether it is valid for this reaction or not. You will get your own answer. Why should I give you the answer when it's written in front of you? Check it out, Mayuk, whether same applies for this reaction or not. यार तुक्का मत मारा करो. तुक्का नहीं. Solve it. Is the reaction question Q coming out to be the same? Beta, I want you to get 180 out of 180 and you are working for 18 out of 180. तुम्हें क्या लगता है जीरो की वैल्यू नहीं होती? Now what is happening? Check it out. The equilibrium constant is y square upon x. On increasing the pressure in the system, it moves down, decreasing the volume. वो काम वही है. The volume is suddenly made half. The concentration of each of the reactant and product becomes double. वो काम सेम है. ठीक है. अब the reaction quotient actually becomes double. Okay. समझ आ रही है बात? तुक्का मार देते हो हर जगह. Here we find that the reaction quotient is twice the equilibrium constant. And if the reaction quotient is greater than the equilibrium constant, then in that case, the reaction is going to shift in which direction? Number of moles increases. Number of moles doesn't increase. Q is greater than K. The reaction goes backward. Backward would mean the concentration of products decreases and the reactant increases. So moles of the product is going to decrease and reactant is going to increase. The reaction is going to go in the backward direction. मायुक क्या कर रहे हो बेटा? बैकवर्ड रिएक्शन प्रोडक्ट साइड में ये मोल्स इंक्रीज थोड़ी ना होंगे. ध्यान से समझो, आराम से समझो, कोई जल्दी नहीं है. नो प्रेशर, आराम से, कूल. बोलो, देखो आराम से. Any confusions here? So this means to attain the equilibrium, the reaction would shift towards the reactant, that is backward direction, away from the product. The reaction proceeds in the backward direction, the product are consumed, the reactant would be formed. यानी कि nitrogen tetroxide N2O4 will be formed and NO2 will be consumed. Welcome, Dr. Karan Raj Sinha. Could you please send your scorecard so we can share the scorecard with the other student? Now, if the pressure is decreased on the piston, we are doing the same thing. First, we increase the pressure. Now, we decrease the pressure. We increase the volume. Now, what happens? If we increase the volume and the volume is made suddenly double, the concentration becomes half of each of the reactant and product. Now, what we get? The reaction quotient also becomes half. Reaction quotient also becomes half. Got it? Okay. So now what we find is if we increase the volume, we decrease the pressure, the reaction shifts in the forward direction. That is towards the product. Any confusions? Any problems? मायूक सेन गुप्ता, कोई रिएक्शन प्रेशर पर डिपेंडेंट है, किस कोई रिएक्शन नहीं. प्रेशर डिपेंडेंट नहीं है इन पर. ओके, रिएक्शन डिपेंडेंट है प्रेशर पर. नाउ वी आर गोइंग टू सी द एग्जांपल्स. यहां पे हमने दूसरा एग्जांपल देखा. यहां पे इफेक्ट पड़ रहा है. Q is less than K, the reaction would be shifting in the forward direction, and then N2O4 would be consumed and NO2 would be formed. Now let's talk about the third reaction. Haber's process of manufacture of ammonia. कर सकते हो इसे, खुद करके देखो एक बार. Do the same thing with this particular reaction. N2 plus 3H2 giving 2NH3. What is going to be the effect of increase in pressure and decrease in pressure on this particular reaction? Whether it's going to move forward or the backward or it does not change. Check it out and tell me. Tell me, tell me. Yes, it is dependent on pressure, but you need to tell me whether it's moving in the forward direction or backward direction, or whether it remains at the same position. So when we increase the pressure, the reaction shifts in the forward direction. Okay? This is the equilibrium constant. This is when we increase the pressure. And we find that the reaction quotient comes out to be less than the equilibrium constant. Okay? What happens when we decrease the pressure? When we decrease the pressure, the reaction moves backward. Increasing the pressure, the reaction proceeds in the forward direction. Decreasing the pressure, the reaction moves in the backward direction. Can you see that? पढ़ लो भाई, पढ़ लो, देख लो, बता दो. कोई कंफ्यूजन किसी को? देखो, अगर कर रहे हो, लिख के कर रहे हो तो सब कुछ समझ में आ जाएगा. नहीं तो सब ऊपर नीचे से निकल जाएगा. कोई किसी को डाउट? गॉट इट, अनन्या? Now, how do we find it, whether it is moving forward or backward? By finding out the value of Q, reaction quotient. Reaction quotient, we find the value and we compare it with the equilibrium constant. And there we find whether the reaction is going to go forward and the back or backward. Okay? अक्षय ठाकुर लिख के कर रहे हो या नहीं कर रहे हो? Now, this is what we need to understand. The effect of pressure on different reactions is different. The first reaction was not affected by pressure. The second reaction, the increase in pressure shifted the reaction in the backward direction, that is the reactant, while the decrease in pressure shifted in the forward direction, that is towards the product. That is for the second reaction. In the third reaction, the reverse effect is from the second. The increase in pressure shifts the reaction in the forward direction, that is the product, while the decrease in pressure shifts the reaction in the backward direction, that is the reactant. Can you see that? और एक बात समझ में आ रही है आपको कि अपने नोट्स बनाना जरूरी होता है। किसी के भी नोट्स अगर आपको मिल जाए उससे कोई बेनिफिट नहीं होता। फूडी कह रहे हैं नो सर रिपीट, अभी अभी अवतरित हुए हैं फूडी आप। व्हेन डिड यू ज्वाइन द सेशन? हाय फूडी, व्हेन डिड यू ज्वाइन द सेशन? अभी भी हो या नहीं हो? सी फ्रॉम द बिगनिंग फूडी। क्लियर? अजीब सा लगता है ना कि पता ही नहीं चल रहा, पता नहीं हमें कैसे पता चलेगा कि कौन सा रिएक्शन फॉरवर्ड जाएगा कौन सा बैकवर्ड जाएगा? हाउ डू वी नो इट? Of course, we can find out the reaction quotient Q value, and then we can tell whether the reaction is going to go in the forward or the backward direction with the increase in pressure. आज इस सेशन में मजा आ रहा है, क्यों? और दूसरे सेशंस में नहीं आता? जहां पे लिखना नहीं पड़ता वहां पे सुंदर सुंदर से वो होती है पीपीटीज, और जहां पे लिखना पड़ता है वहां पे लिखने का मजा आता है। ठीक है ना? प्रियांशु, लिखते रहो, ज्यादा इंटरेस्टिंग लगेगा, मजा आने लगेगा, सो जाओगे। ज्यादा नहीं सोना, पढ़ो इस बारे में। अगर ध्यान से देखोगे ना, द पैटर्न इज ऑब्जर्व्ड। In the first reaction, the sum of the stoichiometric coefficient of the reactant was equal to the sum of the stoichiometric coefficient of the product. There were 2 moles of the reactant, 2 moles of the product, and the reaction was not affected by pressure. Okay? तुम्हें समझ में आ रहा है? बच्चे नहीं आ रहे क्लास में? बच्चे क्यों नहीं आ रहे क्लास में भाई? In the second reaction, the sum of the stoichiometric coefficient of reactant was lower, while the product was more. We were having 2 moles in the product and 1 mole in the reactant. The increase in pressure shifted the reaction towards the reactant. 2 moles in product, 1 mole in reactant. Increased pressure shifts towards the reactant. तुम्हें समझ में आ रहा है? सब कुछ बढ़िया चल रहा है, बट बच्चे नहीं आ रहे हैं, क्या करें? चलो कोई नहीं, बच्चे अलग अलग सेशंस में ज्वाइंट हैं तो इसलिए वो आते नहीं है। अच्छा, इस टाइम पे सीप मैम का सेशन होता है और सारे के सारे उस सेशन में होते हैं। चलो क्या करें, मॉर्निंग सेशन भी तो होता है मेरा, उसमें कौन सा आते हैं? अभी सीप मैम को इल्जाम तो नहीं दे सकते ना कि सीप मैम की वजह से मेरी क्लास में नहीं आते, क्योंकि मेरे तो मॉर्निंग सेशन में भी कोई नहीं आता। ठीक है ना? So increase in pressure shifted the reaction towards the reactant. In third reaction, the sum of stoichiometric coefficient of the reactant was 4, while the product was 2. यानी कि प्रोडक्ट में stoichiometric coefficient कम है. Now increase shifts the reaction towards the product. कुछ समझ आ रहा है? सोच के देखो। 1000 के नहीं, 1 के। अजीब बोलते हो ना, 1000 के स्टूडेंट। 1000 के का मतलब पता है? 883। एक हिंट मिल रही है। इसी में हम तो घर से क्लास ले रही हैं। मिल गया आपको हिंट? अ जनरल फॉर्म। ध्यान से देखो, whenever the pressure is increased on a system at equilibrium with an intention to decrease the volume while keeping the mass constant, यानी कि in a closed system, the reaction will shift towards the direction which has a lesser volume for the same mass, यानी कि the reaction will shift towards the higher density. Check it out, क्या ये सही है? प्रियांशु घोष, भगवान ने मेरे को अगर कुछ बच्चों के लिए डेडिकेट कर दिया तो अनअकैडमी वाले मुझे कहीं और डेडिकेट कर देंगे। ठीक है ना? ये समझ में आया? कैन यू सी दैट दिस पर्टिकुलर स्टेटमेंट? मायूक सेन गुप्ता, हम कुछ ये कह सकते हैं ना कि इट इज शिफ्टिंग टुवर्ड्स द लेसर नंबर ऑफ मोल्स. If the gases are involved, the lower volume is the side which has a lower sum of stoichiometric coefficient of gases. So increase the pressure, the reaction shifts towards the lesser number of moles of gases. समझ आ रहा है? If you have attended the complete session, आपको समझ में आ गया होगा. अगर आप बीच में कूदे हैं तो can't help it. Is it clear? एग्जाम पास में होगा तब तक का इंतजार कौन करेगा बेटा? अनअकैडमी वाले इंतजार नहीं करेंगे उतने टाइम का. They want the student in the channel. Okay, fine. समझ आया ये? चलो अब बताओ. Ice equilibrium with water. If I increase the pressure on this particular equilibrium, which direction will the reaction shift? ये पढ़ो ध्यान से और मुझे बताओ क्या होगा. तुम सुनते नहीं हो. सुनते नहीं हो. Obviously, we are talking about 0 degrees Celsius. Forget about the temperature, whatever it might be. And I said equilibrium. Equilibrium and water and ice, the equilibrium will be established at 0 degrees Celsius only. आंसर दूं? When you increase the pressure on a system in equilibrium having ice and water, increase in pressure shifts it towards water. सुनते नहीं हो, समझते नहीं हो, बस रट्टा मारते हो, प्योर रट्टा. अभी बोला था ना, when you increase the pressure on a system at equilibrium, the reaction shifts towards higher density. Higher density. समझ आई बात? Now let's talk about the effect of the inert gas on equilibrium. So we'll start with the effect of the inert gas in the next class. Tomorrow we have the marathon sessions. Okay? I think अभी काफी है. So the normal schedule is 2 p.m. we have botany, we have 3 p.m. zoology, 4 p.m. we have chemistry with me. Join our Telegram channel for YouTube classes PDFs, t.me/NEET Elixir. NEET Anoop is my channel. And NEET UG subscription, Iconic Plus centers. You can join with us. Get the discount using the code AVLIVE. Join with me. Unacademy.com/Anoop Vashishtha and follow me. I just got Ayan Saha. Sayan Saha has given me a hat. What about you? मिलते हैं 8 बजे. ठीक है ना? Thank you. Bye bye. Evening 8 o'clock in special class. याद से आ जाना. ठीक है? Okay then. Bye bye.